If you're up for all three.
Good evening, ladies and gentlemen. And if I could have your attention, I'd like to welcome everyone to the March meeting of the Madison Astronomical Society. Thanks everyone who's with us here in person at Madison, at UW Space Place. Thanks for joining us here, and thanks to everyone joining us on our YouTube channel tonight. Thanks for being here. Before we start our guest presentation for the month, there is some announcements to go through. And first of all, I bet we've all noticed it was very nice weather today, and then tonight there could be a bit of rain and stuff. So just an opportunity to remind everyone that now that it's spring and there could be some rain and the thawing is kind of all done, the ground could still be muddy. So for those of us who are really eager to go to Vienna Research Station for some observing, please keep in mind that the grounds around the clubhouse and the concrete pads, it could be really muddy, and the places that we normally park our cars could be soft and muddy, and cars have been known to get stuck. So when the grounds are really muddy and soft, please park in the area south of the arborvitae trees and walk your equipment in towards the observing area. Because we have had members get, including myself, although it was during the winter and I drove somewhere, my car got somewhere where it shouldn't have done. You can get stuck, and it isn't fun getting a tow truck out there. Does anybody have any questions about Vienna Research Station? All right. Coming up, speaking of Vienna Research Station, on Saturday, March 29th at 7 o'clock, we are going to have this season's first monthly star party. And some folks have pointed out that this Saturday, March 29th, could be a really good opportunity to do a Messier marathon if you want to try to stay up all from sunset till sunrise and try to see every object in the Messier catalog. You can do it. It can be done. But you have to have a plan. So this could be a very fun star party coming up on Saturday, March 29th. And as usual, if it turns out that the weather's looking dicey that day and we're not going to have a quote-unquote official star party, I will make a weather call by 4 p.m. that afternoon. However, if it's looking, for those of you who might want to live a little bit more dangerously, the place is always open to members. So just because I would say that tonight's official star party is a no-go, that doesn't mean for those of you who might want to do some cloud hopping and stuff like that, feel free to take chances. All right. And then coming up on Friday, April 11th, we are having our next monthly meeting right here. Guest presentation that month is going to be Imaging Quasars and Other Insanely Distant Objects, presented by our own member, Terrence Gensky. I saw Terrence here. Do you want to give people a little bit of a teaser about what your presentation is going to be on?
Yeah, I've only been imaging for a year and a half, and somehow or another I caught the bug that I want to see something that's a long ways away. I think 3C73 is probably the most famous quasar. And then it sort of started steamrolling, and I ended up with a long list of quasars that I tried imaging. So I'll be taking you on a tour of extreme objects and then my attempt to take a picture of every one of them. So
that sounds really great and fun. So thank you, Terry. We look forward to your talk next month. Also coming up, we have a very special announcement regarding the 90th anniversary gala for Madison Astronomical Society coming up on Saturday, April 5th. And for this announcement, I would like to ask John Rummel to come up and address the microphone.
Thanks, Lawrence. Can I make my other announcement first, too?
Yes.
So the other announcement that I wanted to make is that a couple of us are planning a camping trip star party kind of on our own, not really an official MAS event, but just a camping trip to the Merritt Reservoir in Nebraska. Some of you may know it as the site of the Nebraska Star Party. We're not going for the Star Party, we're just going there to camp. So there are probably 3 or 4 of us that have talked about seriously going. If you want information about this, email me. If you don't know my email address, email Lawrence, and Lawrence will forward it to me. The campsite that we're using is the one that's right next to the space where the Star Party is. And this campsite, Chris, where are you? This campsite does not take advanced reservations.
Okay.
You can go and you can sign up at the kiosk, but you can't sign up in advance. And I was telling Chris that I've been camping there for years. I've never needed a reservation. And our camp dates, the dates are May 26th, which is a Monday, through the end of that week, depending upon how long people want to stay. Some people might stay 2 nights, some people might stay 3 or 4. I am going to arrive probably on Monday, which is Memorial Day. And if you know what camp weekends are like on 3-day weekends, people are leaving on Monday. So as you're arriving at Merritt, you might have to fight through the thicket of RVs and boats leaving. Once that day is near the end, we're going to have the place to ourselves, and it'll be cool if it's dark. So camping at Merritt Reservoir in Nebraska, May 26th through 27th or 28th, something like that. Yes?
I just want to say, I've been to the Nebraska Star Party twice. Truly dark skies, no light pollution. It is incredible. You walk the prairie by the Milky Way.
It's a good place. It's really dark. Okay, the gala, the 90th anniversary gala. Some of you might have heard of it. We met with our caterer and our event host yesterday, and for the first time ever for an event like this, MAS has had to impose a cap on registrations. We have limited space, and we have arrived at that limited space. So I've had a number of people already talk to me tonight about getting their checks and their registration forms into us. We are at that point where if you're still wanting to go and you haven't gotten that to us yet, you may be on a wait list, unfortunately. I'm optimistic about the wait list because we've got so many people coming, there are inevitably people who can't make it. And so I do think we'll be able to make use of the wait list, but I think that we are already there. So I'm not discouraging you. Get that reservation form and your check into us, and we will stay in close touch with you because we want everybody to be able to make this. I hate turning people away, but we might be at the stage where we might have to turn some people away. 1 or 2 questions about that? Anybody? Yes?
Dress code?
Dress code is, I'd say casual, but I do think there will be some people who will consider the status of the event maybe a call to take that a notch up. I wouldn't be surprised to see a couple of ties. I think that'll be the exception rather than the rule.
I'll wear a tie.
Pants. I'm going to wear long pants.
I am not going to wear shorts and flip-flops, and that should tell you something. Yes?
Yes, the reason I ask is we were at the American Science Center in Milwaukee, and they had ties there with astronomical themes. They were like $7. So,
Yeah, maybe we
and I bought
might have to have an award for the best tie.
Yeah.
And so, yeah, wear what you want, but feel free to be casual if you're more comfortable being casual. So if you need more information about that, email me. If you don't have my email, email Lawrence. Thank you.
Thank you very much, John. We have 5 minutes before our guest presentation, and I just was interested to know, is there anyone here who has never been to a Madison Astronomical Society meeting before who would like to introduce themselves? Anyone? Just raise your hand if you'd like to introduce yourself. Yeah. And it's okay if you don't want to introduce yourself. Yeah. And since we still have a little bit of time to use up, has anybody done any interesting observing in the last month that they'd care to share with the rest of the members? Rick, is that a...
Sure. Go ahead.
Yeah, you first.
So we got a sea star, and he really, really liked it. So we went to a park near his house during the daytime, and we aimed at the sun. And it took him a little bit to figure it out. And we got to see the sunspots, and it was very amazing, and it looked very nice.
Great job, thanks for sharing that. Yeah, Rick, did you have a little something?
Sure. I told the newcomers this. I was out last night, actually, and I was getting data on a project I've been working on since January, and then one that I'm just starting. And then once that's set, I had a third one that I wanted to image. And then also the lunar eclipse I was getting last night. And I felt like a complete professional. I mean, I had replaced 2 of the computers at the scope because I'd let them get wet and they died. And so I had my new computer there and it was going great. And I got data on all those targets and I got pictures of the moon. And I went to bed thinking, man, this is it. This is professional imaging, right? And woke up to the nice sound of rain. And my comment about pants, I ran out in the backyard in the rain without pants so that I could get the covers on them. But it's all okay. The mount's okay. The primary mirror is okay. The brand new computer is okay. So all is good.
Neighbor's okay.
I told them about it, and the guy kind of did this, and his wife said, "Woo, we should set an alarm, Brian." Which I did have a short thing about apparel.
Okay.
Here, you hold. I'll talk. So there was a bit going around on the mailing list about sizes for some of the apparel. I have the soft shell jacket, which I adore.
And this is for the Madison shop that
Right,
we
right.
have for those of us who
Yeah.
coming
So
up to speed.
what?
Camera.
Oh,
Yeah, show
the camera.
right here.
There it is, with the Gala logo on it. So this is a limited time item. And if you want to see sizing, like I said, I have an extra large and a large. A member has already claimed the large, but she's not here tonight. So
if you're interested in trying on the large or the extra large, just for reference, then yeah, speak to Rick and he'll help you out. Is that right?
And I was not wearing either of them last night with no pants.
Well, thank you very much, Rick. And, yeah, that's every astrophotographer's worst nightmare. I think the one nightmare I had is my first season ever doing video astronomy out. I think it was in the month of December, and I was trying to get pictures of the Horsehead Nebula, and the cold weather condensation inside of my regular laptop that made the display all garbled and stuff, so I went out and bought a semi-rugged laptop after that. So those things do happen. Yes, Walter, I'll be right with you. Oh, that's a bad way to go. I'll have to go the long way around, I guess.
I just wanted to say that the temperatures have finally risen enough in the atmosphere to allow my pressure-sensitive H-alpha telescope systems to work again. In the cold, for some reason, they were not able to maintain a pressure that allowed it to go on band. So for most of the winter, I've been unable to see the sun in the hydrogen alpha, but we're back.
Great, cool. That's great news. All right, well, I see it is 7:30. John, would you like to introduce tonight's, or wait, there's some, oh, you are, okay, you got this down.
Longtime members will know that John usually has the honor of introducing our speakers because John is the one who does the hard work of finding and booking all of them. Today, I will be doing it because I have known our presenter for over 20 years, probably 2003, is that right?
Yeah.
My wife and I were students in the geology department at the same time that Carrie was a graduate student. My wife was also a graduate student at the time, in 2002 through about 2005. And Carrie Eaton has been the curator of the Geology Museum since 2009. In addition to managing over 250,000 individual specimens in the museum's collection, She curates and installs permanent and traveling exhibits, directs graduate and undergraduate students, and facilitates use of the museum's permanent collection for research and education. What's not written on here is she is also now a community celebrity after a new species of trilobite from Wisconsin was discovered and named in her honor, Waukeshaopsis eatoni. And this really confused me at the time, because even though I know that's your name, I still think of you all these years with your maiden name. But it's my, let me read your abstract here. So her presentation today, Wisconsin's Meteorites, Visitors from Space. Thousands of meteorites strike Earth's surface each year, but most go unnoticed because they land in the ocean or in large uninhabited areas of land. Wisconsin has only 15 known meteorite falls or finds, ranging from the Algoma meteorite recovered in 1887 to the witnessed fall of the Mifflin meteorite in 2010. Carrie will share the geological and historical stories behind some of these notable finds, as well as provide an update on the museum's latest acquisition, the Vienna meteorite, Wisconsin's 15th meteorite and Dane County's first ever. On behalf of the Madison Astronomical Society, let me welcome you to our March meeting. Thank you.
All right, thank you, everybody. Am I on? It sounds like I am. All right, so everybody hear me okay? Great. Thank you so much for having me. I'm going to start my talk with a disclaimer, which is that I'm not an astrophysicist. I'm a geologist. And
wait, what?
I know, it's shocking. My geological knowledge is strictly earthbound. And so I'm going to be talking about these objects from space, specifically meteorites, and focusing on the ones that we have on display in the museum, specifically the ones that hail from Wisconsin. But I'm also going to start by giving my talk a little correction, which is that Wisconsin's meteorites are not visitors from space because they don't get to leave once they come here. They stay forever. It's a little bit like coming to Madison and you realize how awesome it is. There's a bit of a gravitational pull. And you get just kind of drawn in. So yes, our meteorites are going to be earthbound for a long time. So I'm the curator of the Geology Museum on campus. We are a public museum that receives over 60,000 visitors a year. 11,000 of those are school kids, all the way up to high schoolers who come through on 1 hour long guided group tours. We've got 5,000 square feet of exhibits and over 250,000 objects in our permanent collection. We're open over 300 days a year. That's something we're incredibly proud of. And equally proud, our admission is free. So if you have not yet been to the Geology Museum, I highly encourage you to stop by. We have also been around for a very long time. Our museum was founded in 1848. That is the same year that the university was founded. At the very first meeting of the UW Board of Regents, they decided they needed to form a mineral cabinet, cabinet being the turn-of-the-century word for a museum, and thus the Geology Museum was founded. So not as old as the solar system, we've been around for a while. This is actually a couple of photos from our museum around the 1890s, and these are both taken in what was a really kind of beautiful Victorian-style museum in what is now the Geography Library. And so our museum was in Science Hall, what is now the new Science Hall, for a very long time until we moved to our current location in 1980. Now, I'm going to assume that almost all the people in this room are going to know the majority of the words that I'm going to use tonight, but just in case, I thought it would be really good to just go over some terminology so that I can then use these technological words with free abandon. So I'm going to guess that most of you are already familiar with the difference between a meteoroid, a meteor, and a meteorite, right? So meteoroids are those large objects out in space. They can range up to about, from tiny little particles, grains, all the way up to about 1 meter or 3 feet in width. Once they enter the atmosphere, then we give it the name meteor. And then this is when the geologists take over, is when this thing lands on the ground. We call it a meteorite. So if it's flying in the sky, it's a meteor. If it's sitting on the ground, it's a meteorite. For the most part, all the meteorites that we have hail from the asteroid belt. That's our meteorite homeland. To date, there are no known meteorites that have come to Earth's surface that hail from Jupiter's Trojans. So all the meteorites that we're going to be talking about are primarily from the asteroid belt, with the exception of the ones that come to us from the Moon and Mars. Now, when it comes to Wisconsin's meteorites, there are 15 known meteors that are responsible for the fall of all the known meteorites in Wisconsin. 7 of those have produced iron meteorites, and we're going to go into that in a little bit. 8 are stony meteorites, and 5 of those are meteorite falls. And if you're not already familiar with these terms, a meteorite fall is one that has been seen or heard, where the stone or stones are usually recovered pretty quickly afterwards, and a find is exactly what it sounds like. It is a meteorite that is discovered later. The meteor itself was not seen. Now, from the very beginning of meteoritical studies, meteorites were put into these 3 bins because humans love organizing things. So we put them in these 3 bins based primarily on their metal content. So if you go back and you read meteoritical bulletins and you read Geological Society of America publications from the early 1900s, they're going to group the meteorites into these categories based on their metal content. So the first one there at the top are stony meteorites. They are, in fact, stony as they sound. They have mineral component to them, and the iron content is less than 20% of that nickel iron. Many of them contain small rounded mineral particles known as chondrules. So that's your stony meteorites. Your stony iron meteorites are very rare. These are the ones that contain roughly equal amounts of silicate minerals, usually olivine, and that iron nickel metal. If you've ever seen a palisite, that's what fits into that category of stony iron meteorites. And the last is that bottom one, iron meteorites. They're the ones that we tend to think of most frequently when we think of meteorites, but they actually only account for about 5% of all known meteorites. They are basically giant hunks of metal, composed primarily of iron, mixed with a little bit of nickel, and small trace elements with things like cobalt and gallium, maybe gold, some iridium. Now, as I mentioned at the top of my talk, I am not an astrophysicist, but it doesn't keep me from appreciating the wonders of meteorites. So this is a photo of me. Actually, we were at a conference, and we were getting a behind-the-scenes tour of the meteorite collection at the Field Museum. This gentleman standing with me is James Holstein, who is the collections manager of the geological collections and manages the meteorite collection at Chicago. And you can probably see that the door is open to meteorites starting with the letter A, but Jim had me go put on a pair of gloves and then come back to present something and walk it around the room, and so I didn't actually see which cabinet he opened. So he pulls out a meteorite, and he starts talking about the meteorite collection, and then he says, "Carrie, would you like to hold this one?" And I said, "Absolutely." And as he hands it to me, he tells me it's a piece of the Allende meteorite, and a colleague of mine from Milwaukee Public Museum takes this picture of my reaction, because I am holding a meteorite that contains pre-solar grains in it, and calcium aluminum-rich inclusions. This meteorite holds the oldest components of our solar system, and as soon as he said the name, I knew it. And I was very excited and also perhaps a little equally terrified. So we're going to go back to that word chondrules, and also I threw out some calcium aluminum-rich inclusions in there, those CAIs. And so this is actually a cross-section of that Allende meteorite. This is a sample from AMNH, the Museum of Natural History that's in New York. But the Field Museum has quite a few pieces of this as well. And so when we talk about chondrules, we're actually talking about these kind of rounded bits here. But first I'm going to talk about those CAIs, or those calcium aluminum rich inclusions. This one here is a really big one, and they can be both rounded and smooth like this one, or they can also have an irregular boundary like this one over here. This is actually another CAI. They tend to form at higher temperatures, and they condense directly from the solar nebula. As a geologist, my earthbound brain has a really hard time imagining what this might look like. So my favorite analogy for this is ice crystals high in the atmosphere. And so you have high in the atmosphere, there's low pressure, you have water vapor, and that water vapor will crystallize directly into ice crystals, skipping the liquid phase. That's effectively what's happening to form these CIIs. You have these elements that are present in the solar nebula, and they condense straight into these crystalline mineral forms, skipping that middle phase. I still have a hard time imagining it because as a geologist, I want minerals to crystallize out of a melt. And that's actually what happens with our chondrules. So those condense at slightly lower temperatures. They actually formed about 1 million years later than those calcium aluminum rich inclusions at lower temperatures. And they actually contain crystals of things like magnesium and silicon and iron, whereas those calcium aluminum inclusions, those CAIs, they obviously have calcium aluminum in them, and then also some oxide minerals and some titanium. So these rounded ones here, you can see some of them have like a little bit of a boundary. Those are your chondrules. And the reason that I want to mention chondrules is because this is how we categorize meteorites now. Again, humans really like to organize things. And so now that our ability to identify meteorites has grown, and even more importantly, our instrumentation has gotten more advanced, we're able to tell finer differences between meteorites and group them by their chemistry, their composition, and their crystal forms. So I love that this is colored. Thank you, NASA, for color coding this. So the first one over here that I'm going to mention are chondrites. I've already used the word chondrules. So our chondrites are undifferentiated meteorites that have chondrules. There are a few different types of chondrites. We're not going to worry about those. And then they're grouped into even further subgroups. All the ones we're going to be seeing tonight are in this ordinary chondrite group. These are the most common of the chondrites, even though chondrites are the most primitive of meteorites. They contain the oldest material from Earth's early solar system. All right, the next group is achondrites. It is what it sounds like, A without no chondrules. So these are another kind of primitive meteorite, but what happens is that alteration, some melting, removes those chondrules. So you have alteration that changes the structure of the meteorite, and these don't have any of those rounded particles in them anymore. Also over here in our differentiated meteorite groups are our stony iron meteorites. Those are our calcites. And then our iron meteorites, and we're going to see a lot of those tonight because iron meteorites are some of the easiest to find because they don't look at all like Earth rocks. Even though they're rare, they're pretty easy to identify because they look so different. Okay. This is I don't like complicated charts. This is a little complicated. So I found this diagram, and it's my favorite because it uses words that I love, for example, like rubble pile. Thank you. Okay, so if you could imagine all of those particles and that dust swirling around in our solar nebula as some of that starts to accrete and you're forming planetesimals, this is when you're starting to create bodies that will eventually become asteroids, that will then eventually break up and then become our meteorites. This picture helps me a lot because when you think of these chondritic meteorites or these chondrites, these are the ones that tend to come from these rubble piles. This is before these bodies become differentiated and start developing layers. So if we think of our Earth as an analog, our Earth has a core that is, we hypothesize, primarily made of iron and nickel. Makes sense? It has a mantle that is comprised of molten rock, and it has a crust. And so we're moving from this kind of accretionary material of this rubble pile towards a differentiated body. And the cores of these differentiated asteroids are what give us our iron meteorites because they're coming from this core right here. So that's where our iron meteorites come from. Now, achondritic meteorites, calcites, especially palisades, you'll get some disagreements on exactly where these come from, whether they are from crystals that are getting reabsorbed into an iron melt, whether they're from a boundary layer between the core and the mantle. Is mantle material getting pulled down and there's mixture somehow at that boundary layer? There's quite a few different hypotheses and arguments about this one. And then stony meteorites are really easy. They're the ones that look most like terrestrial rocks because they come from that outer crusty layer of that differentiated asteroid. Okay. We all doing good? All right. If people want to ask questions, I should say this. If people want to ask questions, please do. Yes.
Oh, you're right with the,
Oh, okay.
I can also repeat your questions.
no, question.
Okay. My question is, how big does an asteroid have to be to get enough compressional heating for differentiation to occur?
Great question. I don't know exactly. Next question. Yeah, you're welcome.
Yeah, Walter will be great with you.
Did I mention I'm an earth geologist?
Walter has a question for you.
Yes, recently I received my first thin section of a meteorite,
Yeah.
and the first thing I noticed was all these beautiful little circles, the chondrites.
Yeah, those are your chondrules.
And
Yeah.
so most of them, in the sample I have, seem to be the same diameter. Is that sort of normal?
They can range in diameter. Some of them will get, a little bit larger and some of them will be a little bit smaller, but no, and that's because those chondrules are coming from, well, think of it as like globs of melt. And so there is a limit to how big that little globule can get before it starts cooling and becoming something else. You also, in those chondrites, you get a matrix that is coming from aggregated solar dust. And that's what makes that matrix. And so there's a limit to how all of that gets bounded together. And so they do tend to have sort of a similar size. Okay. I liked the picture because it helps me, again, as a non-astrophysicist, visualize what this process looks like for us near-Earth mortals. Okay, so that brings us to the first one I want to talk about, which is the Trenton meteorite. It's probably Wisconsin's best-known meteorite. It's the oldest by discovery date. It's a little silly to talk about dates with meteorites because they're all going to be generally about the same age, give or take a million years or so. So whether we want to call them 4.56 billion or 4.57 billion, we're just going to throw around 100 million years like it's no big deal, which for me as a geologist is very weird because it's a big number. So the dates that I'm going to be showing up here obviously are the discovery dates. So this is the Trenton meteorite. It was discovered in 1858. It's classified as an iron. It is a 3AB, so those are Roman numerals there at the front. And that iron meteorite classifications are based on the nickel content and how it plots against those trace elements that I mentioned earlier, like gold or gallium or iridium. One reason why the Trenton became so famous is because one of Wisconsin's most famous citizen scientists became very interested in it. This is Increase Lapham, sitting here studying a piece of the Trenton meteorite, founder of the Wisconsin Academy of Sciences, and a self-described Trenton meteorite obsessive, because every time a piece became available, he wanted to look at it and study it and write it up. And so this little table over here is from the seminal resource on iron meteorites. It's Buchwald's Handbook of Iron Meteorites. It's fantastic. If you're into meteorites, especially iron meteorites, I would highly recommend it because it is both informative and it is exhaustive and describes all of the iron meteorites that have been found. I also like that it kind of shows you the timeline of discovery and where they go. And so you can see here that those first pieces that were found in 1858 Many of them were cut and distributed to museums and institutions across the country. And then later, there was a second little block of discoveries here in 1952 when some folks mounted effectively an early electronic metal detector on a wheelbarrow and returned to the site to gather more of this material. So the first 4 masses of the Trenton meteorite were discovered by plowing, which in Wisconsin is probably the most common way to discover a meteorite. So of all the meteorites that fall onto Earth's surface every day, the majority of them are going to land on the roughly 3/4 of our planet that is covered by water. And others of them are going to land in large expanses of uninhabited areas or in dark forests where it's hard to see them against the dark colored ground. So a lot of these ones that land in temperate climates get a little buried, and they're discovered by tools of mankind. And when we're talking about discoveries in the 1800s, that's mostly going to be by plow. So these are discovered near the town of Trenton, which is about 45 kilometers northwest of Milwaukee, just a little bit southwest of West Bend. More masses, numbers 5 and 6, were plowed up later in the same field and were also described by increased lapum. And then a lot of these were cut and distributed, some of them through Ward's Natural History establishment or Ward's Natural Science, which still exists today. And then we're going to I will also talk about some meteorites that we don't have in our collection and we don't have on display, because as a curator, I have to go chronologically. And so these 2 meteorites, the Vernon County, which was discovered in 1865, and the Hammond, which was discovered in 1884. Vernon County is an ordinary chondrite, and Hammond is one of those iron meteorites, and it's an ungrouped iron. So it is an iron meteorite that can't be classified into one of those groups by some of its chemical similarities. This brings us to the Algoma, which was the one that I mentioned in my abstract, because it is a beautiful iron. This one was discovered in 1887. Does anybody want to guess how it was found? Plowing, great, you're paying attention, just checking.
Also, it says on the slide.
It does. Plowing, yeah. So this one was discovered while plowing a field just 4 miles west of Algoma. This one, obviously another iron, so it has that, what we call meteoritic iron, or iron and nickel in it. And so this is a 1AB group iron, and these little letters that come after the classification, these are little subgroups, so you might have seen some of those boxes on our meteorite chart where I said, let's ignore those for now. So this is a subgroup. So the Algoma was originally published in the Geological Society of America Bulletin, and it was studied by William Herbert Hobbs, W.H. Hobbs, who was a professor of mineralogy at the University of Wisconsin's Department of Geology. So we actually have some of Hobbs' collections in our permanent collection at the museum. So it's pretty exciting that one of our own actually studied and described the Algoma meteorite. And I had to share this because I love this drawing, this illustration from this paper. And what it demonstrates here are the marks that were left behind by the tools of discovery. Because, again, when humans find something weird, we have to poke at it and figure it out. And so a lot of the dents and divots and gouges on the surface of this meteorite are actually from the discoverers taking different tools and implements and trying to figure out what this weird rock was that they had found in their field. So a lot of these dents and divots are from chisels and hammers and rocks. This one over here by the letter C is a file. You can actually, I'm going to go back just so you can see it. So here's that edge that has been filed off a little bit. No, it's okay.
Is that actually a section taken off onto the side there?
Oh yeah, we'll talk about that too.
Okay.
Yeah, it is. We'll go back. So yes, this is a cut piece that has been sliced off the end here. And you will hear, as long as we're, kind of delving into this a little bit, you will hear folks say like, oh, what a shame that they cut that. because it's far less valuable now that it's been sliced. But the only way to classify a meteorite is to cut it. So when you cut it, you learn what it is, you learn more about it, and then that actually also gives it value. So it depends on what value you're talking about. You're talking about the scientific value, the knowledge value, or you're talking about the aesthetic value. There are a few different ways to view it. I don't fall down too hard on either side of the argument. So I'm okay with some curiosity here being left behind on the surface. I actually think that it kind of adds to the story. These horizontal lines that go across the surface, those were made by filing, but there are some real natural marks on this meteorite surface that tell the story of its flight and its descent to the Earth's surface. And so here, by I and H, these are what are sometimes called thumbprint marks. They are called regmaglyphs, and they are from places where that nickel iron surface was melting. So when that body enters Earth's atmosphere and that meteorite starts falling, there is a compression of the air in front of it, and that compression causes an extreme amount of heating, and that actually melts the material. Some of that material will ablate and incinerate, and that's what creates that fireball in the sky. That's what gives it light. We see that as visible light. Some of that material will actually melt and redeposit. So when that material vaporizes, we get these little depressions, these regmaglyphs. When that material redeposits, we get these other marks that are in this diagram that go around the edge here in this radial pattern. And these are flow lines. And you can see it on our meteorite on display. And at the time, they were referred to as drift ridges. We had, like, when this was first described, flow lines, that term did not exist. So it was recognized that they were raised ridges and thus could not have been left by a file or by the workings of the farmer. And what they are is the surface of this meteor melting, and these are effectively cooled drip lines. And what I really like about these physical characteristics is they represent the last instant of cooling before that thing hits the ground or as it's hitting the ground. That's it. That's when that metal is solidifying. That's the final picture we get of this object's travel through our atmosphere. I'm going to go back again. I hate going back in talks, but I'm going to go back again because I want to show you those lines here around the edges and how you can see them. And you can also see that this meteorite has a little bit of a shield shape to it, which is very common for stones that are oriented. That's another meteorite term. It's an oriented stone. And that means that it held largely one position during its flight through the atmosphere. If they move around, their shape can change a little bit. They can be kind of shield-shaped. Like this one was probably spinning some. Ones that stay very stable during their flight and are oriented will actually start to develop the shape of like a nose cone on a shuttlecraft, if you could imagine what that appears like. And those are ones that tend to be very stable. Okay.
It would seem that
Yes.
that hit the atmosphere at the flat side going into the atmosphere the way the lines are.
Yes. So the comment was that it seems like it would have come through with the flat side facing the Earth's surface, and that's correct. The flow lines tend to drip away from the leading surface. Yes.
Can you age it from the melting line from it so you can get it when it fell?
Can you age it from the melting line? No. No. And so there are some that can be dated using radiogenic dating techniques, similar to carbon dating, which is often used for archaeological methods. But when we use radiogenic isotopes to date geological material, we're using methods with bigger clocks. And so that tends to be uranium and lead, because those isotopes decay at such a slow rate, they can go back that far. But you can't really date the time of the melting, which makes it kind of tricky in iron meteorites. Sometimes you can in stony meteorites, and that's because they have mineral content. I thought I saw another hand. Yeah.
How did you find out, what type of test did you use to determine that those striations were from the meteor itself rather than something dripping on it, basically?
Oh, sure. So the question was, how would one determine that these surface lines are from the meteorite itself and not from some other kind of alteration? And that's because these lines are positive instead of being negative. They're not material that's been scraped away. They're material that's been deposited. One of the most common things that comes into our museum to be identified when people are convinced that they have found a meteorite is industrial slag. And when they bring it in, I want to tell them, I get it. I totally get it. Because that industrial slag cools and it pools, and some of it twists and it flows and it makes shapes that look a lot like this. It's not, but it looks kind of like it. Unfortunately, slag also has escape bubbles in it, which meteorites don't have. Sometimes it's from an iron that's not particularly magnetic. That's usually a sign that it's not a meteorite. But I understand why people think that, because it has that kind of depositional melt, which is what's happening here on that meteorite surface. Okay. So someone mentioned the slice earlier. I think that also came from up here in the front. And yes, the Algoma meteorite was cut because one of the other things that you can see in iron meteorites are these structures that are called Wittgenstein pattern. And that refers to the structure of these alloys of nickel iron. However, if we actually look back at the history of publication, we should not be calling them Wittgenstein pattern, even though that's the more common term. We should be calling them Thomson structures, because the first person to publish on this was actually a scientist by the name of Thomson. He was British. He was working in Italy, and he was doing this research where he used acid to etch the surface of meteoritic iron to show the crystalline structure of these different alloys. And his research never made it home because of the Napoleonic Wars. Interesting. So Wittgenstein made the same discovery and published just a few years later and got all the credit. So I guess maybe don't do your research during times of continental war is the message you took away from that. So when the iron is cooling, it first cools and hardens in these cores, right? In the cores of these differentiated bodies. And it starts to form two different alloys of this molten iron. One is taenite and the other is kamacite. And the reason that these kind of intergrowths of these two alloys take this shape is because of the incredibly slow rate of cooling. We're talking about cooling rates between 1 degree centigrade and 10 degrees centigrade per 1 million years. Because it's cooling in the vacuum of space. Whereas if you have molten rock that's coming out of a rift in the crust, or it's coming out of a volcano, that kind of magma that will eventually cool and become a rock that we know as basalt, that cooling happens on the order of maybe days to weeks to months. So very different rates of cooling. When something cools very fast, you get tiny, tiny crystals to no crystals at all. when something cools very slowly, you can actually see these crystals of this iron nickel metal. So this is the Gibeon meteorite. This is another kind of up-close picture of that structure, and you can see that kind of more geometric pattern of those interlacing crystals, actual crystals of this meteoritic iron. So again, we're talking about these kind of metallic minerals. I've already mentioned, you know, folks bring stuff in for ID, and it's understandable how you might find an earth rock that has iron ore in it, or maybe even, you know, small amounts, trace amounts of nickel, although nickel on Earth tends to occur in silicate minerals. So how do we know if we find something metallic on Earth, how do we know whether or not it's a meteorite? And for that, I bring you... I cannot take credit for this flowchart. This actually comes from Randy Curator, who is at Washington University in St. Louis. He has a lovely set of pages all about meteorites and how to tell that your rock is not a meteorite, is the long and short of it. But there are a few instances here where you might hit just the right pattern to have something that might be a meteorite. My favorite is this one that's on the far left edge. Does it attract a magnet? Nope. Is it heavier than other rocks? If you say yes, you go straight to the non-meteorite category. Is it heavier than other rocks? No. Does it have a dark, thin crust on the outside? That's a very important component of meteorites. Yep. Ooh, okay, we're still interested, yeah? Is the inside lighter colored than the outside? Yes. Send me some photos. Because this could be one of those chondrites, where you have lighter color, more crystalline composition on the inside, and on the outside, that dark stuff that you have is called a fusion crust. It's a glassy-like substance that's made almost entirely of iron oxide in the magnetite series, which is what makes it magnetic. But in some of our chondrites, that fusion crust is so thin that it's not super magnetic, or it can also weather and rust, and it loses some of that quality to it. So that might be one rare way where you could end up into the send me some photos and we'll talk about it. But for the most part, this is a standard flowchart. Nope. Okay, so let's talk about that metal. This is the Trenton meteorite again. So more than 95% of all meteorites contain this iron nickel metal. That metal occurs as two different alloys that we saw in those Thomson structures or the Mifflin patterns. The kamacite, which is the one that has the lower nickel concentration, and the taenite, which is the one that has the higher nickel concentration. But you also get trace elements like cobalt, gold, platinum, and iridium, and it's those trace elements that are used to toss those iron meteorites into those different categories. But even stony meteorites have nickel in them. Nickel at a concentration of about 1 to almost 2%. If you found an earth rock that had that much nickel in it, it would be nickel ore. But in earth rocks, nickel is not contained in metal. It's in silicate and sulfide minerals. This amount is many, many, many times greater than practically any terrestrial or earth rock. So if you brought us a rock, it had some nickel in it, but none of that was in a metallic mineral series, we would know right away that you've got an earth rock that happens to be nickel ore. So what we're really looking for in meteorites is this iron nickel composition. And then maybe, you know, if we see some little odd trace elements in there too, that would also kind of seal the deal. This is actually a meteorite that was discovered quite a while ago, but is a new acquisition to our museum. This is the Pine River meteorite, found in 1894. It's an iron, it's another 1AB. And does anyone want to guess how this one was found? Not surprisingly, this one was kept in a farmer's woodshed. It was actually originally used as an anvil for cracking hickory nuts. So it used to be about 6 inches, almost like a 6-inch cube, but eventually disintegrated into fragments because, as we learned earlier, these aren't amorphous hunks of iron. There are crystals in there. And so those crystals have planes and boundaries, and the iron will break. This is not indestructible, iron. This isn't the stuff from superhero movies. It'd be cool if it was, but it will break. So it did actually break apart into many pieces. Those were acquired by a professor at Lawrence College in Appleton. They used to have a pretty big meteorite collection. And then, not surprisingly, through trades and deals and purchases and sales, many of those fragments were distributed. This is really common in meteorites. Some of them ended up at the Smithsonian, and that's actually how we got ours. So our piece of the Pine River that we just put on display recently came to us by way of the Smithsonian collection. Another one you can see in our collection is the Kilbourne meteorite. This one was found in 1911, and this is the first time that we're going to say was not found by a plow, because this one was a witnessed fall. It was seen. Not only is it a witness fall, it was a hammerstone because it went through somebody's barn. So this one actually made its way through the roof and 2 hemlock boards onto the floor of a barn in Kilbourne in Columbia County. It was first heard, and then it was seen, and then it was found. We have a replica of this one. This is a plaster replica. Again, this is the work of Henry Ward, who would run around and collect interesting geological and paleontological samples. Henry Augustus Ward is the founder of Ward's Natural Science. His son, Henry L. Ward, would become the president of the Milwaukee City Museum, which then became the Milwaukee Public Museum. So that's how Milwaukee ended up with a bunch of these, and that's actually how we got our plaster replica as well. And then eventually we were able, through trade, to acquire a few slices of it. And you can see here in the picture, you can make out some of these rounded particles. That's because this one is an H5. This one is a stony meteorite. It's an ordinary chondrite, which is the most common of all chondrites, which you would guess from its name because it's ordinary. The H stands for high iron, and the 5 actually describes the petrography of the sample, how it melts, and the structure of the crystals that precipitate from that alteration. But what I think is really neat is that with some of these stony meteorites, by looking at the composition of them, and then using spectrometry of asteroid bodies and looking at the surface composition of these asteroids, researchers are starting to work out probable or possible parent bodies for some of these known meteorites based on their group. So, I know, it's really cool. So one probable parent body for the H group is this S-type meteorite, Hebe, 6 Hebe, because it was the 6th asteroid that was observed. This is a lovely high-quality photo from ESO's Very Large Telescope. This thing's really far away, so it's okay that it's kind of blurry. But
Looks good to us.
it looks great. Hebe's over 200 kilometers across. So this is one that got differentiated because it's got crusty parts that it can kick out to us as chondrites. I saw a hand. No? No? Okay. Maybe you were just stretching. We're going to keep going. The plow strikes again. This is, we do have a question. Yes.
Can you go back to slide?
I sure will.
Why does it say 1911 and then 1916?
Why does it say 1911?
It says it's hit in 1916 according to the placard there.
Oh, yeah, because I forgot to change the date on my PowerPoint presentation. Points to you, because sometimes cut and paste yields dividends. Yeah, so no, great catch. So Kilbourne, 1916. We're going to just really quickly Angelica meteorite. This one is 1916, the plow strikes again. This one is a 3AB, so that's an iron. We don't have any of this, but Milwaukee Public Museum has a small piece. The largest mass of this is actually at the Oshkosh Public Museum. And if you didn't know, they actually have a collection of meteorites. It's called the Buckstaff Collection. We have acquired some of our meteorites through trade with them. And there were some that I asked for that I was told no. So you'll have to go there to see them. I want to talk a little bit about the Colby meteorite. It's an L6. This is another type of chondrite. This time the L is standing for low iron. The 6, again, describes how it's been metamorphosed and how those mineral compositions come out as pyroxene and orthopyroxene. But we're going to skip all that because I want to tell a little feel-good human story, which is that this is another observed fall. This meteor fell in the evening around 6:30 p.m. near the town of Colby, the same place where they make the cheese, on Independence Day. So they were having a big 4th of July parade, and this is in the evening, but it's summertime, so it's still light out, but this thing was so bright that you could actually see the fireball, and it fell west of town, and people went running to find it. And when meteorites are found quickly, they don't rust. They're not exposed to moisture for as long, and so that fusion crust stays intact a little bit better, a little bit longer. And as often happens when meteors are observed, they draw crowds. And so, of course, none other than Henry L. Ward went rushing up there to collect some meteorites for his museum. And so here's a piece that's in the Milwaukee Public Museum, and here's ours, and you can see those chondrules there in that chondrite. And at the time, he promised the people of Colby that he would make replicas and distribute pieces that could be displayed at the Colby Public Schools, and for whatever reason or another, that never happened. So this gentleman actually reached out to me, Keith Kleinstick, and he's an amateur astronomy observer and actually also a master electrician. And he actually wrote a really great article about kind of the Colby meteorite and some of this experience. And so he reached out to myself and a collection manager at Milwaukee Public Museum, Patricia Curl-Burke, about whether or not we would be able to make some replicas for them to have on display in their public library in a little display on the history of Colby. And I said, sure, why not? So Pat said, well, we're not sure how to do the replicating. And I said, well, let's just 3D print it. So she scanned, why not? She scanned her meteorite and sent me the file. We scanned ours, and with the help of our museum scientist, Dave Lovelace, we printed them. And so here's the 3D print of our meteorite. And I said, well, that doesn't look like a meteorite, and this is not a thing I do well. So then we mailed our 3D prints back to Milwaukee Public Museum, which is known as the home of the artistic diorama. So they just happen to have some really great artists in-house, and so they painted them. And so down here are the meteorite replicas. They look so good. They're really excellent. And so these replicas were sent to Colby. This is Vicki, the Colby Public Library Director. She's holding ours. And this is Keith, and he's holding the one from the Milwaukee Public Museum collection. So it only took us about 100 years to make good on this promise. But we finally did it. Okay. This is a bit of a callback to the Mount Morris meteorite, or back to the Pine River meteorite. This is the Mount Morris meteorite, which was discovered in 1937. It was originally described as its own distinct meteorite. It was described as an achondrite, which is one of those kind of weirdos from the differentiated side of the chondrite meteorite. So it's one that doesn't really have chondrules, but it's got silicate minerals. And for a long time, it was thought to have been its own meteorite find. Not a whole lot is known about the history. There were 3 fragments of not very much. It was less than a kilogram. They were recovered sometime before 1937. It was recorded in the British Museum's catalog that these pieces were distributed. And then, starting in the 1970s, researchers started looking at pieces of this Mount Morris meteorite and recognized that the composition of the meteoritic iron that was present was almost identical to that of the Pine River. So if we go back to our handy map, you can see that these two are super close to each other. They're about 8 miles apart. So one hypothesis is that the Mount Morris meteorite is actually a silicate-rich inclusion of an iron meteorite, and that it broke off during entry, and thus would have had a different descent pathway, which could describe why its find locality is about 8 miles away. Other hypotheses are that these are different, distinct meteorites. So maybe we put an asterisk on the 15? I don't know. It's just I think it's an interesting study, and it's kind of interesting to consider that these two might have been pieces of the same meteor, of the same piece that fell to Earth. Probably likely that these two are pieces of the same parent body, since their meteoritic iron is so similar in chemical composition. How those two pieces were separated geographically, we'll probably never know. And so in the official meteorological bulletin, which is where all meteorites are classified, they will remain separate entries. So we're going to say we have 15. Okay, that brings us to the Belmont. And we have a very small piece of the Belmont. This one was discovered in 1953. It's an H6. It's another ordinary chondrite, found by plowing on a farm near Belmont. And Platteville got half. And so if you've ever seen this piece on display in Platteville, it was at a time at their mining museum. Then for a while it was in the kind of history portion of the kind of main building at UW Platteville. And then the other portion of this half was cut and distributed. Okay, this crash course is nearly coming to a close. A couple more Wisconsin meteorites. These are 3 we don't have. Would love to acquire them. First is the Zenda. It's an iron meteorite, another discovery by Plow. This 1961 Oshkosh meteorite was a stony meteorite that was actually found by a hitchhiking college student. This discovery is a little dubious because this person also talked about wanting to find a meteorite their whole life, and then they just happened to find one while hitchhiking in a farm field. So they're either like the luckiest person alive, or maybe there's something else going on there. And then this other one is the 1996 Turtle Lake. This one is actually an observed fall because it hit a parked car and punched a hole through its windshield. So that actually made it pretty easy to find because you had a really great collecting agent, which was a car. But somehow, part of the original stone was never recovered. The pieces didn't quite fit together right. Where did it go? We'll never know. So, not too long into my time as curator at the UW Geology Museum, we had our own exciting meteoritical event. Some of you in this room may have seen it. Yeah. In 2010, there was this fireball in the sky, the Mifflin meteorite. Here it's still a meteor. In 2010, and as it broke up, its debris trail was actually seen on radar. When you see these bright flashes like this is actually that meteor breaking up, and that happens way more commonly with stony meteorites than iron ones, because if you think of a stony meteorite and you think of all of those grains and those mineral components, each one of those grains and minerals has a boundary, and each one of those boundaries is a potential pathway or nucleus for fracture. And so stony meteorites tend to break up and create these big fireballs. So at 10:07 p.m., on April 14th, the night before my husband's birthday, there was this bright fireball and explosion over southwestern Wisconsin. And eventually, about 70 stony meteorites with a combined weight of about 8 pounds would be recovered across this landscape. Like I mentioned earlier with observed falls, it created a frenzy. The Wisconsin State Journal dubbed it meteorite mania, and they were not wrong. The very first piece of this meteorite that was discovered fell on a farmer's corrugated roof of an outbuilding while he was standing outside. He heard it hit, and then something hit the gravel right next to where he was standing. No joke. So then he looked around and he saw this little black rock that was very different from all the gravel next to his outbuilding, and he brought it into the Geology Museum the very next morning, on the morning of the 15th. And we all joked with each other. We said, oh man, did you see that fireball? The phone's going to be ringing off the hook today. Everyone's going to think they found a meteorite. So this piece came in, and my colleague, Brooke Norstad, looked at it, and she said, I think it might be a meteorite. And I said, get out of here. We've looked at so many meteor rungs. There's no way that somebody actually found a piece. What are you talking about? And then she showed it to me, and I, oh gosh, actually. So our museum director, there were only 3 of us working at the museum at the time. Our museum director, our assistant director, actually went out to this farmer's property, and they were followed by a news van who'd been staking out our museum. I actually went out the next day, and the director and I were on a farmer's property, and we were sweeping the field in an organized fashion, looking for potential meteorites. And it was so weird because I kept looking up, and across the road from us on another farmer's property was the Discovery Channel, and the meteorite men were over there looking for meteorites just right across the street from us. This is absolutely surreal. And one reason was that it was so visible. And what's playing now in that bottom right-hand corner is screen capture from the camera on top of the Atmospheric and Oceanic Science building, which is right next door to our building, AOS. And when I had seen that they had managed to catch this on their camera stream, their folks sent us these images, and so these play on loop in our display of Wisconsin meteorites.
But it doesn't show the beautiful blue-green neon, like I'm going to die color.
Yeah, those incredibly bright colors that come from that vaporizing of that material as it's melting and then immediately ablating. So we have several pieces of the Mifflin on display, and we were actually proudly the first museum to display the Mifflin meteorite. I mentioned earlier oriented stones. Oh, is this driving you guys crazy? Is it because I'm moving a lot?
It just started.
I sometimes hypothesize that it might be static or something.
All right.
Is
it better?
Yes.
Okay.
It's not you.
Okay, it's not just me. Okay.
Keep moving.
I'm moving too much. Okay. So I mentioned before oriented stones. So this is an oriented nose cone, and you can see that it's taking that really perfect nose cone shape. This is the leading edge. This would have been this point would have been facing the Earth's surface as this little tiny stone hurtled towards the Earth's surface after it broke apart. And you can see here how there's like a slightly thicker rim here along the edge. This is where that ablating material is pooling up. And if we were able to look at the backside of this, it would actually roll over and cool on the backside. That's called a rollover lip. So this one was so cute that it also made the newspaper, talking about how we had 8 pieces of the meteorite on display. I think it actually ended up being 9. because we had many people would just bring pieces that they had found to our museum to add them to the exhibit. We were going to be displaying them for this 1 week. That was right around the time of our annual open house. And this one woman called and said, oh, I have this meteorite. I'd love to put it on display. And so I peeled myself out of bed and got to the museum at like 7:30 in the morning so she could hand this off to us and put it on display. But one of the larger pieces, it's not the largest piece that came from this fall, but one of the larger pieces that we had on display that week is this one here. It's about 1/3 of a pound, so it's 142 grams. You can see this beautiful fusion cross, and I actually love that it has a little corner chipped off, so you can see that more crystalline chondrite on the inside. You can see how, people might think their igneous rocks are meteorites. If they're heavy, they're dark on the outside, they're light on the inside. Some of that dark might be a patina, but this is that glassy fusion crust. One thing that wasn't in my introduction is I'm a bit of a hard sci-fi geek. And so I was particularly excited to learn when this event happened that the plausible parent body for this particular meteorite was featured in a series of novels that I really like, which are the James S.A. Corey Expanse series of novels. And the possible parent body for this group of chondrites is Eros. So again, looking at those chemical compositions and trying to pair them with these large asteroids based on the reflectivity of their surface material. Eros is only about 34 kilometers across, but apparently still large enough to be a little differentiated. Now, you might think, as a geological curator, that having a meteorite, a real genuine meteorite, come into your museum is a once-in-a-career kind of thing. And I thought that too. Until the summer of 2023, when a farmer called the director of our secondary ion mass spectrometry lab, or SIMS lab, and said, I reached out to some folks after that 2010 Mifflin meteorite because I had this weird rock that I found in the summer of 2009 that doesn't seem to be like any of the other rocks on my farm. And, he hadn't heard back, and just really wanted to learn more about this rock. And so he reached out to the director of our SIMS lab in the summer of 2023, and she said, well, I know who you need to talk to. And she looped in the museum director and myself. And this is one of the first pictures that we saw. There were other pictures attached to this email, and our director looked at this one and he said, yeah, that's a meteorite. Not surprisingly, this one was also discovered by plowing. Yeah, and this is actually the nick from where the plow struck this meteorite. And I can tell you from personal experience that this edge is sharp. This is peeled back, bent metal. It turns out that the farmer's brother-in-law is also a professional metallurgist. So they actually sawed off a small corner, and he took it to his workplace where he etched it, and he looked at it under SEM and said, yeah, I'm pretty sure this isn't an earth rock. They ended up shipping a piece of this to the Field Museum, hoping to get it classified and identified, and it sat for years until we were contacted in 2023, and we just went out right away. Well, you're just down the street from us. So we went out to their farm. This whopper comes in at 109, just over 109 pounds, so 109.5. It's an iron meteorite. Of course, you gotta visit the horses while you're there. And it was through the great generosity of these farmers, Jim and Jan Cook, that we were able to work towards getting this meteorite classified and finding a way to put it on display at our museum. When we had first started, we weren't even certain that we were going to be able to acquire this museum. We thought maybe we'll get to put it on display for a weekend, for our open house, kind of like we did with all those Mifflin stones. This is Noriko Kita. She's the director of that SIMS lab. This is our museum director, Rich Slaughter, and myself. And we were just really fortunate that the Cooks were such kind and generous people. So Noriko and Rich and I decided that we were going to push the cart from behind and work with the Field Museum folks to get this meteorite classified. Now this all took quite a while to sort of figure out whether or not we would be able to acquire the meteorite, and then working on the description with the folks at the Field Museum. And we were approaching the campus-wide celebration of the university's 175th anniversary. Well, we were also founded in 1848, so our annual open house was going to be a celebration of our 175th anniversary. And wouldn't it be cool if somehow the universe helped us out and these two events could coincide? And so we did actually propose this classification to the Lunar and Planetary Society Meteoritical Bulletin, and we asked them to embargo it until just a few days before the campus-wide celebration in our museum's open house. So the main mass comes in at just under 50 kilograms, or around 110 pounds. This is a photograph of the whole main mass. It has some really beautiful surface structures, which are hard to see because of the rusting. And I'll go into that in a little bit because we actually wrote the physical description for this. One of our contributions obviously was just going out there and georeferencing it. So we went out into the field with the farmers. They told us about how they found it in the summer when they were going to be planting alfalfa. We walked out to the spot where, Jim remembered encountering it, and we took the coordinates because coordinates are required as part of that. And this is really only about 13 miles away from our museum. It happens to be close to the town of Vienna. And so we really wanted the meteorite to be named to Vienna. Meteorites tend to be named by the closest town or municipality. Sometimes they're named after a geographic feature if that name is already taken. So for example, with that Mifflin meteorite, which ended up being named Mifflin, the closest municipality was actually Livingston, but there's already a Livingston meteorite from Montana, so that name was not available. So that's why that one's named Mifflin. So we were really angling for Vienna because the name of the farmer's farm is the Vienna Echo Farm. Eck is EQ for equestrian, and the O is HO for horses. And so we were really hoping that it would work out, that it could be named Vienna, so that they'd always kind of have this tribute to them and their farm and their discovery. And so it was, weren't sure that it was going to get approved, but the name did end up getting approved. The type specimen is actually going to reside at the Field Museum because they ended up doing the geochemical analysis on this one. This is part of the submission, the Vidmich-Stoughton pattern. I'm not going to get into argument about what we should be calling it. But you can see here, this one's been acid etched, and it's been stained, and sure enough, you can see those lamellae, those bands of those iron-nickel alloys. So this is just like a small little piece, and that's going to stay at the Field Museum. This is the only plot that I'm going to show this entire talk, and this is just about the classification of its iron type. Okay, I'm going a little long, I'm sorry. The only thing you really need to take away from this plot is that the plots are trace elements. For this one, it's gallium, and over here we've got cobalt. And if we look over here at our legend, you can see that each of these symbols is representative of a specific meteorite. These North Chile ones I think they're actually 2AB irons, so I'm not sure why those are reference points. But down here are group averages of some of those groups of iron meteorites. And you'll see here that the analysis of the Vienna is a blue plus. And down here is the light blue square of the iron group 4A. And so you'll see over here in the trace element gallium versus cobalt plot that those are practically right on top of each other. And over here in our copper gold plot, they cluster really closely together. And that's what yields the classification of a 4A. So again, here's the geographic location, very, very close to Madison. It just so happens that the very first school group tour, after we put this on display and we had our open house, happened to be from the town of Dane, which is right up there, right next to Vienna. And so here were these kids who came to our museum and they got to see this meteorite that had been discovered right in their backyard. Okay, so its classification is an iron 4A. These are cumulates from the core of a small asteroid that probably broke up about 400 million years ago. One of the neat things is that there are other really well-known 4As, some of which are on display in our museum. So the Vienna has a little bit of a cousin or long-lost sibling in the Gibeon. I showed this to you earlier as a really excellent example of those Wittgenstein patterns. The Gibeon is also a 4A iron. The Vienna has some really great surface features. It has a slight pyramidal shape because it is slightly oriented. So this point up here was the leading edge, but it was probably tumbling and rotating some, which is why it never really developed a strong nose cone shape. You do, however, see signs of ablation and deposition on the meteorite surface. So up here you can just make out some really faint flow lines. Those aren't the best ones though. And then over here you see these kind of bumps, these little dimples, and these bumps are actually called splatter marks, and they are places where little blobs of melt is deposited on the surface. If you could imagine sort of like speckle painting something, that's effectively what we're doing, but with molten meteoritic iron. This is right along one of the transitions from the leading edge to the trailing face. This is what one of those rollover lips looks like. So this is where that melt is sort of accumulating and cooling as it wraps over onto the trailing side. And then this is probably the best example of flow lines on the surface, and these ones are trailing away from this tip, this kind of leading point up here on the top of the pyramid, and they cool in place as these raised ridges. All right. I feel like I should stop there. Okay.
Keep going.
These aren't the only meteorites we have on display in the museum. I'll do these real fast. Okay. We also have the Canyon Diablo, one of the most famous meteorites of all time, also one of the most ubiquitous. You go to a museum that has meteorites, they're going to have a big hunk of this because its primary mass was so huge. So if you find yourself, I always like to joke, if you find yourself standing on the corner in Winslow, Arizona, you'll be about 18 miles away from where this thing fell. It created Meteor Crater in Arizona, which you can just see in the photo in the background there. Meteor Crater is about 1 kilometer wide. And the original mass of this meteorite was probably about 160 feet or 50 meters across. This crater, you can actually do radiogenic dating on the kind of shocked minerals around the perimeter of the crater to get an age of this crater. And it was formed about 50,000 years ago. So that's when this big meteorite struck. Another lovely one we have on display is one of these super rare palladites. So we have a little slice of the Esquel stony iron meteorite from Argentina. And I'll start a little video here where I'm kind of tilting it back and forth so you can see those transparent olivine crystals. Palladites are so beautiful because of that olivine. And then how obviously it is mixed in almost equal quantities with that beautiful meteoritic iron. But this is not the rarest meteorite that we have on display. That honor goes to this one, which is the Tessent. It is a Martian meteorite, and it is also slightly oriented, and you can see these kind of cooled flow lines on that surface. This is a witnessed fall. So in the middle of the night, this bright fireball was witnessed in Morocco. And some of these eyewitnesses happened to be nomads who went out into the desert to collect these pieces. And that's why there is no rusting in this fusion crust. So these Martian meteorites come to us when the surface of Mars is struck by large asteroids or other impactors, and it breaks up parts of the Martian crust and ejects them to a point where they reach escape velocity and re-enter space and then become potential meteoritic material. This one is really fabulous, and it is actually the only piece of Mars on display in the state of Wisconsin. Just a little nod to us there. So if you have not yet seen this on display, I would highly encourage you to come explore the UW Geology Museum. And then here's a little bonus. If you ask for me, you can also ask for Richard Brooke, because they like doing this too. But if you ask for Carrie and you say, I saw Carrie give a talk at MAS, and it was really great, and I love meteorites, and the museum's so cool, you could hold a piece of space. So as part of this program, I give all this credit to our assistant director, Brooke Norstead, who created this program called Holding Space. And the idea was actually to take material around to retirement homes, targeting folks who might have seen the lunar landing on TV as children, and to give them an opportunity to basically kind of educate them on current studies of meteorites, and then give them an opportunity to actually hold space. So we purchased, through some funds, we purchased a piece of the Canyon Diablo, again, very common iron meteorite, one of the more ubiquitous ones. And then, this is so cool, she also purchased a piece of the moon. And so this is a lunar meteorite. It has this very large, so it's a breccia, it has this large kind of feldspathic class on one face. And so if you swing by the museum and pay us a visit and drop some names, you can have an opportunity to hold a piece of the moon as well. It's pretty cool. That's it. Thus ends my overly long talk.
We have time for maybe a couple of questions for Carrie. Yes, Rick?
So the first one is, when you got the meteorite from Eros, did you check it for protomolecule first?
Oh, I should have. Yeah, I didn't.
Stay away from
Maybe
me.
I'm infected.
And the second thing is, you talk so blithely about trades and acquisitions and deals with it. So do you actually have the Indiana Jones hat? Because I can totally see it.
Yeah, and our storage looks just like that warehouse where they keep the Ark of the Covenant. Yeah. We've got one back here, but I will not forget you.
Okay. I have to bring this up because you did not.
Yeah.
And I'm going to tell you a little story quick because I want your opinion on this.
Okay.
Some years back, in of all places, Sky and Telescope magazine, there was an article about a man who found a micrometeorite in a stream.
Yes.
That launched a frenzy of goofy people like me searching the downspouts of big buildings.
I was going to say, did you go up to your roof?
Yes,
Yeah.
all of that. And I found a lot of metallic particles that I looked at under the microscope, and they were not what the picture showed as these micrometeorites.
Yeah.
Number one, do you have any micrometeorites in your collection? Number two, what do you think about this whole thing of trying to find them without going to Antarctica?
Yeah. So no, we don't have any. We did actually try. Same deal. We went up to the roof of our building, which is super flat. And we thought, what a great little collection zone. Also collected lots of metallic particles. We're actually right next to the Charter Street power plant, which used to be a coal-powered power plant. So we found lots of stuff that were not micrometeorites. Do I think they're out there? Yes. Do I think they'd be easy to find on our roofs? Probably not. And it's really because of industrial pollution. That it's just too difficult to find those, proverbial needles in the haystack. Yeah. Did you still have a question up here?
Oh, when you said that to get these crystalline structures, it took like more than 1 million years of cooling to occur?
Yeah.
How does it take so long to cool? Is this the interior of a very large object?
Yes, because we're talking about the core of a very large differentiated asteroid.
Okay.
And it's not cooling in 1 million years. It's cooling 1 degree centigrade over 1 million years, which is just so incredibly slow. I cannot even picture what that looks like. My little Earth brain can't handle that information.
There is a second Martian meteorite in Wisconsin.
No!
It's in our museum.
So these are the folks from Earth Haven.
Earth Haven up in
Yeah.
Florida.
So if you ever find yourself up there.
It's very tiny. Very tiny.
All right, well, you've taken away my claim to fame here, but how great actually that you have a piece up there. Earth Haven Museum is a fantastic collection of some great geological material, so if you find yourself up in that neck of the woods, you should absolutely check it out.
Where is it?
Gillett, Wisconsin.
North of Appleton.
About 3 hours from here.
Well, all right. Well, Carrie, thank you very much for a very fascinating and yeah, excellent presentation.
Thank you so much.
As a token of our gratitude for your visiting us tonight, I would like to present to you from Madison Astronomical Society this very fine coffee mug. Just a reminder, coffee mugs do not strictly have to hold coffee in
Oh
them.
no, it's gonna hold all kinds of things, and I will cart this around the geology building with pride. And the
Thank you so much for being here, and I'd like to thank everyone else for coming here tonight. We're going to close up the room here at Space Place at about 9 o'clock, and we want to invite you to next month's meeting on Friday, April 11th. So we hope to see you then. Have a good night, everyone, and have a good weekend.
For those of you here in